Alright, hey, today we are here with Natural Wonders Chapter 16. And Natural Wonders 16 is another chapter all about astronomy. And to start off Natural Wonders 16, we are looking at the HR diagram. The HR diagram is just a diagram, it's a chart of stars, and they're graphed based on their temperature, or really what ends up being their color, and their luminosity or their brightness. And so yes, color does also represent temperature, where kind of the reds and oranges are kind of lower temperature, then everything that's white and blue would be a much higher temperature. And then also brightness, where the bottom of the graph is very low brightness and the very top of the graph is very bright stars. And the video that you're going to see is really cool. It's taking just a snapshot of space. So just an observation of an area of space, the sky, the night sky. And it's taking that observation and it's arranging it based on their temperature and their brightness. And so you can see how the stars kind of sort themselves out into specific groups, and those groups are ones that we saw last week with stellar evolution, like the main sequence where the sun is located. And then we also have those red giants in the top right hand corner, and they're bright because they're just so large, but they're very cool. They're that red color. And then we have blue giants that are both very bright and also very hot. And then also white dwarfs, which is what the sun will turn into, and that's down in that kind of lower left hand corner. They are very warm, they're very hot, a white color, but they're very dim, very low brightness, just because they're so small. Moving on from the HR diagram, we're going to look at a whole bunch of different types of possible galaxies. And to classify and organize our galaxies, we use something called the Hubble classification system, or the Hubble tuning fork, because it kind of looks like a tuning fork. Have you ever seen one of those? The first type of galaxy we're going to talk about are elliptical galaxies. And these galaxies are usually made up of older stars, and there's less new star formation, meaning there's a whole lot less dust and gas compared to other types of galaxies. So this potentially might indicate that it's an older or more evolved galaxy than some of the other ones we're going to see. And kind of a cool thing about these elliptical galaxies, that although they're usually smaller and maybe not as bright as some of the other galaxies like spiral galaxies, we're ending up finding more and more of these as we look harder into space. The brighter galaxies, the larger galaxies are the ones that stand out to us first, but through more and more studying, we're actually seeing that there's a lot more of these elliptical galaxies out there than we initially thought. And I think that's pretty cool. The next type of galaxy is a spiral galaxy, which includes our galaxy, the Milky Way. And right now it's the most numerous type of galaxy, these spiral galaxies. And these spiral galaxies are consisting of a lot of younger stars and a lot of dust and gas that would end up producing more stars later in its life cycle. And although this seems to be an area where a lot of new stars are being created, there's typically a central bulge, like a bunch of older stars in the middle of that spiral galaxy. So it is made up of both younger and older stars. The next type of galaxy is a barred spiral galaxy. And there's some similarities here with that there's still a lot of dust and new stars, and it also includes a central bulge of older stars. But now that central bulge extends out to the sides to make a more or less straight bar extending out from the center of the galaxy. And one theory about this bar in a barred spiral galaxy is that it acts almost like a funnel, funneling stars and material in towards the central bulge. And when it comes to these spiral galaxies, barred spiral galaxies are more common than just a normal spiral galaxy. The last type of galaxy we're going to talk about is just simply an irregular galaxy. And these galaxies end up being a category of galaxies that just don't fit the pattern of any of the galaxies we've already talked about. And oftentimes these irregular galaxies, they form through an interaction of galaxies, nearby galaxies, either colliding or just pulling at each other with their gravity. And that changes the shape, maybe from spiral or barred spiral or elliptical to being something else. So when we talk about what a irregular galaxy might look like, it doesn't really have any particular pattern. Next in chapter 16 is the Doppler effect. And the Doppler effect might be something that you've heard about before, but it's really either the compression or kind of the stretching of waves of energy based on movement. And to start off, there's the example of a car and the car's horn. And you can tell in the video that as the car that's laying on the horn passes by, kind of the pitch, the sound the car horn is making changes. And that's due to the fact that as the car is traveling, it's traveling away from the sound it's creating, stretching out that sound wavelength. And it's traveling into the horn, the sound, the blasting noise it's creating. It's traveling into that as it's moving forward. And that compresses the sound wave. And that compression or pulling and stretching of sound waves, it sounds different to our ears. The way this relates to stars is the same idea can happen with wavelengths of light. So if a star is traveling towards Earth, it's going to be compressing that wavelength of light, and then we can observe that change here from Earth. And same thing, if a star is traveling away from Earth, it's going to stretch out that light wavelength and change the color that we observe from Earth. Which brings us to the next couple features of chapter 16, which are a red shift and a blue shift. When we look up at stars, we can see what we call spectral lines, which is kind of like the rainbow, but it's only certain colors of the rainbow being released from a star, or maybe the light traveling through the atmosphere of a planet. And we know what this pattern of bright lines or spectral lines would look like through different types of gases and from different types of stars. We know, and we can test it right here on Earth. But when we look into space, that's not always the pattern that we see. Sometimes those bright lines, those rainbow stripes, those lines are shifted to one side or the other. Maybe they are more red in color than we expect, or maybe they've shifted towards the blue side of the light spectrum. And that's what we're talking about here with a red shift or a blue shift. Those bright lines are shifted more towards the long wavelength or red side of the spectrum if a star is traveling away from Earth. And those wavelengths, those bright lines, are shifted more towards the blue side of the light spectrum or the shorter wavelength if a star is traveling towards Earth. So observing these red shifts and blue shifts actually can give us a whole lot of information about movement of objects in space. And that brings us to the Big Bang, the formation of our entire universe. And the Big Bang is probably an idea you've heard about before. And it's this idea that everything starts in a very small area, very big release of energy that sends everything flying and creates galaxies and atoms and everything that's here now. And some evidence for the Big Bang is what we just talked about with the redshift. One of the big ideas with the Big Bang is this idea of an ever-expanding universe, meaning that it is just growing in all directions all the time, meaning objects in space are traveling away from each other, and we're traveling away from the center of the universe where the Big Bang occurred. And that's why when we look out into the universe, almost every object we see out there, we observe a redshift or a shifting of the bright lines towards the long wavelengths. And that means it's traveling away from us using the Doppler effect. And so this redshift that we observe throughout almost the entire universe is evidence for the Big Bang. And the last part of our Natural Wonder 16 is again evidence for the Big Bang. We call this cosmic background radiation. So the Big Bang was a massive release of energy. And so that massive release of energy produced a lot of heat in a lot of different ways. And you can kind of think about this microwave background radiation as the leftover residual heat from the Big Bang. And we all know that if you take a pan of brownies out of the oven and put it on the countertop, that pan isn't going to instantly be cool as soon as you remove it from the oven. It takes time for that heat to dissipate. And the amount of energy and heat that was produced in the Big Bang is, I just can't comprehend it. And so it makes sense that that large amount of energy takes a very, very long time to reduce and kind of cool off. And that's really what this background radiation is. Anywhere we look in the universe, we can observe and measure this background radiation that was leftover energy from the Big Bang. And that's it. That's going to wrap up Natural Wonders chapter 16. Make sure you're taking some notes, and if you have questions, please make sure you ask.